This is our final video, section 10.4. We're still working with Fourier series. Let f be a piecewise continuous function defined from 0 to L. Calculating the Fourier series of f may be troublesome because the function is not defined from negative L to 0. Recall that our Fourier series needs to calculate integrals from negative L to L. But if our function is only defined from 0 to L, this may be troublesome. Suppose additionally that f is an odd function. So we know that if the Fourier series were to exist, that it would only be written in terms of sign. So I'm looking at something like y equals x cubed. We know x cubed to be an odd function, but it's only defined from 0 less than x less than L. So I want to perform some sort of extension to this to define it from negative L to 0 to maintain its oddness. So I could extend it in this way, where negative f of negative x is how I define the graph from negative L to 0. And what this extension will do with any odd function is it will create it exactly as you envision it. But the thing is, I just assumed this was an odd function based on what it looked like on one side of the y-axis. All I knew was that it was a curve rising something like this. But if I were instead interested in turning this into an even function, I could use a different extension to accomplish that. You don't know if something is even or odd or anything else just based on what happens on one side of the y-axis. You can define the extension so that whatever symmetry you like occurs. So while this will accomplish your odd extension, you could just as well place an even extension on it, where we would use f of negative x to calculate our values from negative L to 0. Let's look at this in practice. Consider the function f of x is equal to 1/2 x from 0 to pi. So we know what 1/2 x would look like over the entire Cartesian plane, but we're only defining it from 0 to pi. Now, if we extend it to negative pi to pi, we could use the odd periodic extension, and that would give us exactly what we would envision. You would just keep it going, keep the straight line going, keep 1/x going, because 1/x is an odd function. If you take this odd function and extend it in an odd way, you continue to get an odd function. But we could instead extend it using the even periodic extension. And that would look like this, which we would know as having more of an absolute value feature to it. So there are, of course, infinitely many possible extensions. These are just two of them, where you can take something on the right-hand side and you can give it this kind of symmetry or this kind of symmetry or anything you want. There are two other additional ones that are sometimes useful. Sometimes it's useful to add pi on the left-hand side. This would obviously be sometimes useful with trig functions. Or you can just have it equal to 0 on the left-hand side. That just intrinsically seems like you would make the calculation simpler, as if you're calculating half as many things. Okay, so if we define f from negative L to 0 in such a way that the function is either odd or even, we can simplify our calculation of the Fourier series because we know a portion of the integral will be equal to 0. So using that, we can say that the Fourier cosine series of f of x on 0 to L takes this form, where the ANs are calculated as usual, although I will point out this used to be a 1/L, and this used to be a negative L to L. But the amazing thing about these Fourier cosine series and sine series, as we briefly discussed last video, is if you take some odd function f and multiply it by cos and sine, you'll make half of it odd and half of it even. Well, the half that's odd, that integral is 0, and it just disappears. Notice how there is no plus bn sine. That all just going to 0 because of how we define our extension. But the other half that isn't odd, it turns even. And what we get to do with even is Instead of going from negative L to L on the integral, we can just multiply the whole thing by 2 and go from 0 to L, because we know the symmetry of an even function dictates that the integral on the left will be equal to the integral on the right. So we can just double the integral on the right. So the Fourier sine series does the same thing. If we define our extensions in this manner, we can actually eliminate this whole an cos business, because that all is going to go to 0 because of the odd function rule, the integral of an odd function rule. And when we're calculating our bn's, if f times cos is odd, then f times sine is even. And for an even function like this, we know that the integral from negative L to L is the same as 2 times the integral from 0 to L. So that's where this 2 and this 0 come from to simplify the calculation. Okay, now let's use this. Compute the Fourier cosine series for f of x is, and we've got a piecewise function here, f of x is equal to x minus pi from 0 to pi over 2, and f of x is equal to x plus pi from x over 2 to, from pi over 2 to pi. So we'll start by drawing this graph. So we start like this, going from negative pi up to negative pi over 2. But then when we reach pi over 2 as an x value, it's going to suddenly change into x plus pi, which is going to look something like this. And then, as we discussed before, you could make this periodic. And we discussed the convergence theorem last time about how it may deal with these values here and tell you what they're actually equal to. But that's not what we're doing right now. Right now, we're just calculating the Fourier cosine series. So L is equal to pi, because we're from 0 to pi is what is defined. So we are going to extend this to negative pi to pi. That's why we're using a cosine extension here. So a sub n is 2 over L, the integral from 0 to L. This is just our equation we just defined, the cosine series. We're going to plug in pi for L. But also, since it's piecewise, we have to break up this integral. The first half from 0 to pi over 2, and the second half from pi over 2 to pi. Now, we're going to expand this into x cos nx minus pi cos nx. So we're going to end up with 4 pieces here. And 2 of them are going to integrate fairly simply without any further steps. That's going to be the pi cos nx here and the pi cos nx here. So we've just taken those first 2 and we put them up here. So the integral of pi cos nx is pi over n sine nx. And we'll evaluate that from 0 to pi over 2. And then we have the same thing here. It's just the bounds are different. We're evaluating from pi over 2 to pi. But now what's left is this x cos nx here and here. So we need to do an integration by parts. In the last video, we did a substitution and then an integration by parts. We should be able to just do an integration by parts. So let's look at this. We want the integral of x cos nx dx. So we are going to let u equal x, and then du will equal dx. dv is going to be cos of nx, and that means v will be that integral, which will be 1 over n sine x. The dx will go right here. If we want to check that, we would say First, we have to write it down correctly. Sine of nx. If we want to check that, we would say, what is the derivative of 1 over x sine nx? Well, it would be cos of nx times n divided by n. So it would just be cos of nx, which is exactly what we want. So that's how you can do this in one step instead of the 2 steps from last video. And that's what we get here. We take our u times v, so that's x over n sine nx. And we're going to do that twice, once with each set of bounds, once from pi over 2 to pi, and once from 0 to pi over 2. And then these integrals will be the same. It's just v du. So that's 1 over n sine nx, and that's going to be the same on both sides. We just have different bounds. Now, we're going to start plugging in our values here. So sine of 0 is just going to be 0. Same with sine of n pi. So those just go to 0. So all we're interested in are the sine of n pi over 2's. So they're going to come down here. But there's actually 2 of them, negative 2 of them. We have a negative pi over n sine nx here, and we have a negative pi over n sine nx here. So it becomes negative 2 pi over n sine nx multiplied by this 2 over pi gives us negative 4 over n sine n pi over 2. So that's what this whole thing becomes when evaluated, and you can check that yourself. Becomes this value. So now as for the rest, sine of 0, of course, is just going to go to 0. So all we're interested in is this sine of pi over 2. Over here, we have the same problem where sine of pi is just equal to 0. So we're only going to be interested in the sine of pi over 2. So we are going to get 2 over n times sine n pi over 2. Because when I plug in pi over 2 for these x values, look at how that pi over 2 cancels perfectly with that 2 over pi. And the same thing will happen here. So they disappear, and all that remains is this 1 over n. And when you combine that with the fact that we have 2 of these, it's going to become 2 over n, sine n pi over 2. And now all that remains are these integrals, 1 over n sine nx. Well, that becomes 1 over n squared cos nx, and of course the negative flips. Same thing will happen over here with the negative flipping, and we'll get the same integral. So now, when we plug in our zeros, our pi's, or pi over 2's, when you plug in pi over 2, quite the opposite of what happened with sine, these cos values will just go to 0. So we're not interested in what happens when we plug in pi over 2. We're only interested in the 0 and the pi. So here we get 1 over n squared cos of pi x. And here we get 1 over n squared cos of 0. Notice how these two combined to just leave us with negative 2 over n sine n pi. Now we get into the trickier part where cos of n pi can be simplified. As we discussed before, cos of pi, cos of 2 pi, cos of 3 pi, cos of 4 pi. It's just going to bounce back and forth from 1 and negative 1. So this just becomes negative 1 to the n minus cos of 0 is 1. Now, when we plug in an even value for n, something interesting happens where we get cos of 2 pi, or sorry, sine of 2 pi over 2 would be sine of pi, which is 0. And if I plug an even number in here, I get 1 minus 1 is 0. So for any even value of n, this whole thing just goes to 0. Now, when we plug in an odd number, it's not so simple. But we lost half of the terms right there, because if you plug in an even value of n, it's all 0. It becomes 0 plus 0 equals 0. So this is kind of our solution. We're going to plug it back in to get that f of x is related to a naught over 2 plus this sum. Now we just showed that if n is even, the a value is 0. So this a naught over 2, that just disappears. That's 0. So we have that it's related to this. Now, why have we brought in this 2k minus 1? Well, we want to eliminate all even values of n. And if n is odd, then the definition of odd is that it's equal to 2k minus 1 for some integer k, whereas the definition of even would be that it's equal to 2k for some k. So if you want to only express the odd values, you can replace n with 2k minus 1. So we are going to let n equal 2k minus 1, and we are going to start plugging in values. So if I plug in k is equal to 1, that is going to give me my a1 term times cos of 1, x. So the cos of 1x is here. And I would go back to my definition and see what happens when I plug in 1. I get 2 over 1 times negative 1 raised to the 1, which is negative 1, minus 2 over 1 squared. Note also, this power arises because we want to find some way to express the fact that if I plug in an odd number, I want to know when this is going to be odd and when it is going to be even. So I get my negative 2 minus 2. So that's just going to be negative 4 for the first one. And then as you plug in more and more values, you begin to see that we have an alternating sign here. And we have the denominators going up to n and n squared repeatedly. And this is our Fourier series.